Well, congratulations! You made it through crazy chapter 4. So now we can start on chapter 5 and we can do some discrete random variables. So, probably something you haven't heard before are the words random and variable put together. And maybe or maybe not, I don't know. So, let's talk about what a random variable is. So, basically, the short version random variable, it's a quantitative variable like x or y or something whose value depends on random chance. Okay, like rolling a die. Roll a die, we have a numerical value 1 through 6, and it depends on random chance. Okay, choose somebody out of the class, their age, how old they are, that depended on random chance because it depended on who was chosen from the class. So we're going to start with a discrete random variable. And that is a random variable whose all possible values are discrete. We remember what discrete is. Discrete are where things can be listed in some way. Most of the time, it's things that are counted. So that's most of what we're going to be doing, or things that are counted, like how many siblings somebody has, what's your household size, how many classes are you taking, anything like that. Anything that all the possible values can be listed, and it usually counts. Most of the things we do are counts. How many telephones are on your cell phone account, anything like that. But discrete random variables can do other things. Of course, dice rolls are discrete, and shoe sizes are discrete, even though they have halves. You have 3.5, 4, 4.5, 5, blah, blah, blah. Those are still discrete. So we can do anything that can be counted is discrete, even if it is infinitely countable. Usually we just have a few set of numbers, but there is a couple of distributions that are actually infinitely countable, but after you get past a few numbers, it's basically the probabilities are nearly zero, so we kind of ignore them. Okay, so let's talk a little bit about what a probability distribution is. So probability distributions are a list of all the possible values of your discrete, so that's why you want to be able to have it listable, and their corresponding probabilities. So that's one way to do it. It's usually like a little table. Usually we have x, and then we have the probability that it equals x, and so we just make a table out of it. Or another way to do it, we can also have a formula. So we can have some kind of the probability of x equals some kind of formula that spits out a probability. So similar to this first page that I have right here. This is the P machine, so we put a bunch of stuff in it of information. It is a formula, spits out a distribution. So it can tell us, and we can also use this to create this listing, which we'll be doing when we do binomial. So the named distributions we'll be doing this with. We have about 3 named distributions that we actually have a formula that we can do this with. So we're going to be using the probability distribution, and we can actually create a probability histogram, pretty much a relative frequency histogram, but it's with theoretical probabilities, so it's a little bit different. Because if you think about, remember the theoretical probability, if I rolling dice is perfect, but if I actually roll the dice 30 times or 50 times, I'm probably not going to get it exactly like that. My relative frequency is not going to be exactly the same. So our horizontal axis is, of course, our random variable. Our vertical axis will show the corresponding probabilities. So let's look at an example of this. So here's a probability distribution for the random variable x, the number of siblings of a randomly selected student in a finite population. So perhaps one class or a couple of classes or what have you. So the siblings that were had in here, the probability someone had 0 siblings was 20%, 1 sibling was 42.5%, 2 siblings 27.5%, 3 siblings 7.5%, and 4 siblings was 2.5%. Nobody in this example, in this finite population, had more than 4 siblings. So the probability histogram looks like this. Now you can also talk about the shape of it. Does anybody see a shape in there? Start thinking about that. The tail is going off to the right, so we would call this a skewed right probability distribution. So we have a skewed right probability distribution, and we can easily make this. So you'll note that this is in the center of each bar because we're looking at something that is discrete and easily counted. And we have single value grouping, which is normally how we do probability histograms. So let's talk about two dice. Here is the probability distribution for the sum of two dice. This is the probability distribution, mind you. And you have to be careful here because, of course, if I were going to roll dice a bunch of times, I'm not going to get exactly 1/36 of the time. I'm going to get 12. If I roll a dice 36 times, chances are that's not going to happen. Or if it does, now all these probabilities aren't going to be exactly right. Even if I get this one maybe right, I'm not going to get all of them exactly right. I would have to roll dice for infinity in order to get these theoretic probabilities exactly right. And I really don't want to do that. So let's think about this. So we can easily find the probabilities. What is the probability of 7? Well, it's right here. It's 1/6. Let's do some more probabilities. What's the probability that y is greater than 7? So that's the probability I roll something greater than 7. So it's one of these. So it's this one, this one, this one, this one, plus this one. So I have to add all of these up. So I'm going to add 5 out of 36 plus 4 out of 36 plus 3 out of 36 plus 2 out of 36 plus 1 out of 36. Okay, that's not very hard. So that is what? 15? Yeah, 15 out of 36. Or divide them both by 3, and I get 5/12. So if you want to roll a number greater than 7, you have to roll. That has a chance of 5/12, a little under a half. So here's a good point that I want to make, is that the probability for any probability distribution, the probability of every possible thing added together is 1, which makes sense. The probability that something happens, that is the only things that are possible to happen. So if we roll 2 die, we're going to get between 2 and 12. We're not going to get 1. We're not going to get 13. So the probability that one of these things happen, one of these 11 numbers happen, added all together, should be 1, which makes sense. So using that information, what do you think the probability that y is less than or equal to 11? Well, let's think about that for a second. Less than or equal to 11. So that would be all of these added together, right? Okay, does anybody feel like sitting there and adding all those together? No, but we know complementation rule, right? So the only one that's left out is 12. So the probability that y is less than or equal to 11 is also equal to 1 minus the probability that y is 12, because it's the only one left, which is 1/36. So it's 35 out of 36. So much, much easier. So always look for that if you're doing these problems, because sometimes the complementation rule makes the problem a lot easier. So now let's go back to, remember, the family with 4 kids. And so here we have x counts the number of girls in this family. So what's the probability they have 0 girls? That was 1/16. Remember, that was the probability they had all boys. The probability they have 1 girl, remember there were 4 ways out of 16, which makes 1/4. This was 6 out of 16, or 3/8. Oops. This one was 4 out of 16, or 1/4. That's the probability that they had 3 girls. And the probability they had all girls was 1 out of 16. So what is the probability they have exactly 2 girls? 3/8. What's the probability they have greater than or equal to 2 girls? That's going to be these three added together. So remember, this was 6. I'm going to go back to 16 so that I can add them all easier, which was 11/16. Less than or equal to 2 girls. Well, that's these numbers, which are, well, the same numbers, only backwards. So again, same thing. What is the probability they have between 1 and 3 girls inclusive? You're going to see that word inclusive. It just means we're including the endpoints here. That's going to be 4/16 plus 6/16 plus 4/16, which is 14 out of 16, which is going to be 7/8. What is the probability x equals 0 or x equals 4? So that means they have basically all the kids are the same gender, which we already did this problem. That is going to be 1/16. Since these are mutually exclusive and this is a union, we can simply add the probabilities. So we get 2/16 or 1/8. And you'll notice that these two are complements of each other. So we could have done this one could do 1 minus the other one. 1 minus 7/8 is 1/8, and 1 minus 1/8 is 7/8. So we could have done that way also. Okay, so next section. The mean and the standard deviation of the discrete random variable. So here we have this family with their 2.5 children. Here's their 2 children. Here's their 0.5 right here. Yeah, that doesn't really happen because, of course, averages don't work that way, right? So let's talk about the maternity stay again, revisited. So I want to talk about this, and I kind of want to think, what is the average length of a maternity stay? Now my question, can we just add up 1, 2, 3, 4, 5? I mean, is it 3? Possibly. But there isn't the same number of all of these. If this was the same number of everything, then the answer would be 3. If these were all weighted equally. But these are not all weighted equally. We can't just add them up. Okay? Because there's actually, this one happens 11.8% of the time. This one happens this much. So we actually have 15 ones plus 32 twos plus 56 threes plus 19 fours plus 5 fives. So we have to add up all these numbers. We have to add 1 15 times. So 1 plus 1 plus 1, or 15, plus 64, plus 56 times 3, that's 168, 76, and 25, over 127. So that's how we would find that average. So it's exactly the same thing. However, I want you to think about this a different way. These numbers over here, remember this is 15 over 127. This one is 32 over 127. So if I simply do this, if I go 1 times 0.118, really all I'm doing is 1 times 15 divided by 127 plus 1 or 2 times 0.252. All I'm doing is 2 times 32 over 127, etc., etc. So if I divided each one of these up, and I could very easily do that, this is the same thing as saying this is over, each one is over 127. Then what I'm really doing is just taking each possible value times its frequency. So it's 1 times, I'm going to take this whole thing over 127. It's 1 times 0.118 plus 2 times 0.252 plus 3 times 0.441 plus 4 times 0.15 plus 5 times 0.039. These two things are going to give me exactly the same answer. So this is 0.118, 504, let's see, 3, right, okay. That one's 0.6, so it's pretty easy. And this one is let's see, 5 to... I don't like that one. Not doing that one in my head very well. 0.195. Okay. And now if we add all these up, plus 0.6 plus 0.195, we get 2.74. So we actually do get the real average. It's a little bit under 3 days because these are weighted differently. Now, this doesn't mean that there's any maternity stay that's 2.74 days, or maybe there is, but that's not the way this is actually done by the number of days that calendar days they were in the hospital, and not done that way. So what we have is, we think of this as kind of like the law of large numbers, 2.74. Of course, nobody stays that, but if you take, say, 1,000 women, the average length of stay is going to be about 2.74 days. So this brings me to the formula for the mean of the discrete random variable. All you have to do is take each value of x times its probability and then add it all up. Now remember, order of operations means you have to do this part first before you do the addition. So you take each value, multiply by its probability, and take the sum. Now this is also called expected value, and it can be denoted by E of x like this. Just another way of writing it, but it's exactly the same thing. No difference. And this formula looks different, but it really does take that theoretical frequency of each possible value of x into account. And that is the really big difference, and it's kind of what we just saw in that last example. So let's think of another one. Consider the mean number of heads in 3 tosses of a fair coin. Well, we know that the probability of getting 0 heads is 1/8, right? Because it's 1/2 times 1/2 times 1/2, so that's 1/8. Well, that's going to happen 0 times, that's 0 heads times 1/8. And remember 3/8, remember that is 1/2 times 1/2 times 1/2. And then that can happen 3 ways, because you can have head, tail, 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 head, tail, or tail, tail, head. And then this one, 1/2, the same thing, right? Times 3 ways, because you can have head, head, tail, head, tail, head, or tail, head, head. And then, of course, you have your one way of getting 3, because that's just tail, tail, tail. So that's 1/2 times 1/2 times 1/2. And then, so if you multiply all these together, you get 1.5. Now, I say, if you try this experiment once, you will not get exactly 1.5 heads, right? If you toss 3 coins, it's not going to happen. You're going to get 0, 1, 2, or 3. You're not going to get 1.5. But if you try this experiment, say 10, 100, 1,000 times, you might get, in the 10 times, if you do 3 coins 10 times, you might get 15 heads out of your 30 coins. You might get 150 out of your 100 of your 300 tosses. You might get 1,500 out of your 3,000 tosses. So this brings me to this interpretation of the mean of a random variable. If you have a large number of independent observations, the average value of those observations will approximately equal the mean. The larger the number of observations, the closer the average of x tends to be, which kind of makes sense. If you only do it 10 times, you could easily have 22 heads and only 8 tails. It could definitely happen. But if you do it more like 1,000 times, you're going to be much closer to that 1.5 average. This is called the law of large numbers. So let's investigate this using dice rolls. So the average of a dice roll is 1 plus, and this is all. The reason that you can do it this way is because all of these are equally likely. So you can just add them up and divide by 6. So you have the 3.5 is the average dice roll. So if you roll this dice, now each one of these colors is a different one. So like the purple one, they obviously got a 5 the first time. So on the first roll, they got a 5. So the average dice roll was 5. So once they did 2, it went to something else. And then you can see as they go on. But what are they all converging to? And you can see this one, obviously it looks like they got a 3 and then a 2. But this one actually goes downward. They all do something crazy. But notice that the average dice roll, they converge as n gets larger and larger, closer to 200. Look what happens. They all converge into 3.5. And if you did 500 dice rolls, they would even do it. You'd have to even zoom in farther to see the difference. So let's talk about the standard deviation. Now, very similar to the mean, we can also find the standard deviation. So here is the definition formula. So we take the difference between x and mu, so each point and its mean, then we square that, and then we multiply that times its probability, and then we take the square root. Same idea, okay? Because remember, all we're doing is this is the frequency divided by the total anyway. So that's all we're doing right there, is we're multiplying that by the frequency over the total. And an easier way to compute it is this right here. You can actually just take each data point, square it, times its probability, and then subtract off the mean squared, and then take the square root. It's a little bit faster and easier. Okay, again, this is the same thing, just taking a different thing into account. So let's look at the standard deviation for the number of tosses. So in this case, I'm going to take 0 times 1/8, 1 times 3/8, because 1 squared is 1, 2 squared is 4, 3 squared is 9. And then I subtract off the mean squared. Blah, blah, blah. Magic occurs. I get 0.866. And in the case of the family with the 4 children, if I want to find that one, same thing. I go 0 times, well, right now I'm finding the mean. So 0 times 0.0625, 1 times 0.25, 2 times 0.375, 3 times 0.25, 4 times 0.0625, and if I add these numbers up, I end up with 2. So in this part, I need to do x squared. So kind of remind myself up here what x squareds are. So now I have 0 times 1 times 0.25, which is here, 4 times 0.375, 9 times 0.25, and 16 times 0.0625 minus my 2 squared. So this adds up to 5. This is 4, so I end up with 1. How nice. So the average number of girls in a family is 2, no kidding, with a standard deviation of 1. And here's how we look. Now, one of the reasons that I wanted to do this one is because this one is so simple to see. Now, let's say I want to label this. So I made my probability histogram, and I've labeled the mean. Now I want to label 1 standard deviation away, 2 standard deviations away, and 3 standard deviations away. Now let's think about how many events are there. So within 1 standard deviation, I cover 3 out of the events. Okay, so I cover these 3. So I'm within 1 standard deviation of the mean let's see, what is this? Well, 1 to 3, which was what? 7/8, right? Within 2 standard deviations of the mean, I have everything, because I'm covering 0 and I'm covering 4. So I have everything within 2 standard deviations of the mean in this case. That doesn't always happen. So the question is, can this be done on a calculator? So the answer is absolutely. So the way we're going to do this is we are going to first, you have to open your lists. In list 1, we're going to enter all the possible values of x. List 2 is going to be all the probabilities. And then we're going to do a 1 var stats, list 1, list 2. Or again, if you have a menu, you put in list 1 for the data. List 2 is the frequency list, because that's going to be the probabilities. And we calculate. Now, x bar that comes up, that's our mean. That's our mu. Our calculator doesn't know that we're dealing with 3 erratic probabilities and populations. So it just tells us x bar. It doesn't know that it should be a mu, but that's what it is. And then we have to use sigma x because we're dealing with populations. S of x will be blank in this case because n is 1. And the reason that n is 1 is because if you add up the frequencies, which are really probabilities, they should equal 1. So let's look at this maternity stay example, and let's find we're going to do a lot of things to it. We're actually going to find the mean again, and we're going to find the standard deviation. Then we're going to look at the histogram and 1, 2, and 3 standard deviations away from it. So let's go to our calculator. Now, step 1, we want to open our lists. So go to Stat, Edit. In list 1, I'm going to put all the possibilities of x. So the days of stay. 1, 2, 3, 4, 5. And then in list 2, I'm going to write down my probabilities, my relative frequencies. 0.118, 0.252, 0.441, 0.15, 0.039. Okay, so now I have that done. So now I'm going to do my 1 var stat. I'm going to go stat, calc, 1 variable statistics. Now my list is just list 1. My frequency list, second 2. Because I want the frequency, I want it weighted by this amount, and hit enter. Now, as you can see, it gives me x bar, which I'm going to write down as mu. And you can see that S of x is blank because n equals 1. So I'm going to use sigma of x, which is 0.981. So really, really simple, really, really easy to do that on the calculator. So let's create ourselves a histogram, a probability histogram for this. Let's see, we've got 1. Let's see, 0.1, 0.2, 0.3, 0.4. So one day was 0.118. So just about like that. Oops, my 1's not right in the middle, is it? Come on, go away. Okay, 1, 2, 0.252, so about halfway there. And then 3 was 0.441. Go a little higher. Okay, and then 4 is 0.15, which is right here. And 5 is 0.039, so about a third of the way up the first one. Okay, so now we want to label where everything is. Now 2.74, think about this piece right here being 2.5. So where this line is about 2.5. So 2.74 is going to be right here. So I'm going to say this is my mean. Let me get a different color here. So this is my mu. So I'm just going to do a line right here. So that's where my mu is, about right there. So then 1 standard deviation away. So to get 1 standard deviation away, I'm going to go 2.74 plus 0.98 and 2.74 minus 0.98. So 2.7, oops, decimal, plus 0.98, and then I'm going to change this to minus. Okay, so this is 3.72 and 1.76. So looking at 1 standard deviation away, I'm going to change colors again. And I'm going to look at, well, we're going to put this one in red. So we want 3.72, so that's about right here. So this is mu plus a sigma. And mu minus a sigma. So now we want to go up again. We want to go 2 standard deviations away. So we're going to take these numbers and we're going to add another 0.98. And we get 4.7. So let's change to another color. Look at green for 2 standard deviations away. We got 4.7, so we're this one. So we're in here. So that's mu plus 2 sigmas. And if we take 1.76 minus, so we're going to go another 0.98 outward. So minus 0.98 is 0.78. So we're going to be here. Mu minus 2 sigmas. Okay. And I'll need that again in just a second. But I wanted to look, well, I want to go one more. So here I'm done. I've covered everything. If I go one more, I'm actually going to go negative. If I go another negative 0.8, I'm actually going to go negative 0.2. So I'm not even going to go out there. However, if I can go another 0.98 here, then I'm actually going to go to 5.68. So we'll just label that real quick. I'll do that in gray, 5.6, which is actually going to be here. So this is where mu plus 3 sigmas would be. So now I can kind of use that information to look at my data and see how my data is distributed. So how many do I have? I've covered within 1 standard deviation, I've covered 2 and 3 within a standard deviation. So if I add these two up, I have 3, 9, so 69% of my data is within 1 standard deviation of the mean. So then I look at 2 standard deviations away. I covered 1 now and 4. So I've covered everything but this last one. So what's 1 minus 0.039? I think we already did this. 1 minus 0.039. That is 96. So 96.1% of my data is within 2 standard deviations. And then all data 100% within 3 standard deviations of the mean. Now this doesn't always happen. This usually only happens, something like this, only happens with relatively symmetric bell-shaped data distributions. So there we have it. Okay. So that's all for now. We'll talk next time about the binomial distribution, and I will see you guys in class.